All right, let's get right into it, because this is a big one. For the very first time, physicists have managed to connect two of the absolute strangest and most powerful worlds in quantum mechanics. We're talking about the ticking, rhythmic world of time crystals and the supersensitive realm of optomechanics. This isn't just another experiment. It's like they've built a bridge between two completely separate continents of physics that have never been connected before.
So to really get our heads around this, let's start with a pretty wild question. You know how the atoms inside a crystal, like say a diamond, repeat themselves in this perfect, stable pattern across space, right? Well, what if a material could do that but in time? What if its atoms could just tick back and forth in a perfect rhythm all on their own, forever?
Well, that's exactly what a time crystal is. It's this really enigmatic phase of matter where the atoms just naturally oscillate in a stable, repeating pattern. And the key thing is, it's not because you're pushing them or zapping them with energy. It's just a fundamental property of their state. They literally have their own internal clock. For the longest time, these things were just fascinating but totally isolated curiosities, just kind of existing in their own little quantum bubbles.
Think about it. A system that moves in a repeating pattern forever without any energy input. I mean, that sounds an awful lot like a perpetual motion machine, which, is supposed to be impossible. Now, let's be super clear. They aren't true perpetual motion machines. They still have to obey the laws of physics, but just making that comparison really tells you how bizarre and special this whole concept is.
So the huge question for scientists was, how on earth do you interact with one of these things? How do you talk to a time crystal that's totally isolated? Well, to understand the really clever solution they came up with, we first have to look at a classic idea from physics, a kind of light and mirror trick.
And that trick is called optomechanics. Basically, it's the whole field of study about how light, that's the opto part, and tiny little physical movements, the mechanics, can actually influence each other. And it's an incredibly powerful toolkit. It lets scientists make some of the most mind-bogglingly precise measurements you can imagine.
Okay. So here's the basic idea. Just picture a box with a mirror at one end that's on a tiny spring so it can move. First, you shine a beam of light into the box. Believe it or not, the pressure from that light actually pushes on the mirror and makes it wiggle. And here is the absolutely crucial part. As that mirror wiggles, its movement changes the properties of the light that's bouncing off of it. So by measuring the light that comes back out, you can learn everything about how that tiny mirror is moving. The two are connected, they're coupled.
Right, so what did the researchers in this experiment actually do? Well, you guessed it, they built a microscopic, quantum-sized version of that exact same system. Except their light and their mirror were much, much weirder.
And this is where it gets really wild. In their experiment, the light wasn't light at all. It was the time crystal itself, specifically a bunch of magnetic ripples called Magnons, all ticking away in perfect unison. And the wiggling mirror? That was the rippling surface of a superfluid, this bizarre quantum liquid that flows with literally zero friction. So in the real lab setup, you've got a container of this superfluid helium. Then you have these magnetic coils that trap the time crystal, this little blob of energy, right next to the liquid surface. The whole idea here is that when the liquid surface ripples and moves, it should, in theory, directly affect the ticking of that time crystal trapped right beside it.
Okay, but that's the theory. How do they actually prove it? How do they prove that the rippling liquid and the quantum clock were really influencing each other? How do you even listen for that kind of connection?
I mean, that's really the key challenge in any experiment like this, right? You've got two incredibly fragile quantum systems. Are they truly linked up, or are you just seeing a bunch of random noise? How can you be absolutely 100% sure that they're actually talking to each other?
The answer, it turns out, is you listen for a harmony. This is the actual data from their experiment. So that bright peak you see in the middle, that's the main note being played by the time crystal, its natural ticking frequency. But look what happens when the liquid surface starts to ripple. You get these smaller peaks called sidebands appearing on either side. These are totally new frequencies that only exist because the two systems are interacting. It's like one instrument playing a steady note, and then another one starts vibrating next to it, creating this new combined harmony. This right here, this is the smoking gun. It's the definitive proof that they're connected.
So, what does this all mean for the future? Well, as the researchers themselves put it, this breakthrough removes the experimental barrier between time crystals and other phases of condensed matter. Now, condensed matter is just the physics of solids and liquids. So what they're saying is that time crystals are no longer just these isolated novelties that we can only look at from a distance. We can now actually connect them to things, interact with them, and, well, use them.
And that opens up a whole new world of possibilities. So why does coupling these two incredibly strange quantum systems actually matter? What can we do with this new ability?
It matters because you're essentially combining the best of both worlds. Time crystals are unbelievably stable and coherent. Their ticking is incredibly pure and reliable. On the other hand, optomechanical systems are insanely sensitive to the tiniest little disturbances. So you put those two things together, and you have just created a fundamentally new kind of scientific instrument with power we've never had before.
And by combining this incredible stability with this incredible sensitivity, the potential applications are just staggering. We're talking about things that could help us tackle some of the biggest challenges in all of science, like building ultra-sensitive detectors to search for the faint whispers of gravitational waves, or maybe even to hunt for dark matter. This could also give us new ways to solve a huge hurdle in quantum computing, which is how to reliably store fragile quantum information. The possibilities are really, really stunning.
You know, for decades, time crystals were just a dream in a theoretical physicist's notebook. Then, for a few years, they were a delicate curiosity in a lab. But now we've officially made contact. We can listen to their rhythm, and we can watch how that rhythm dances with the world around it. And that just leaves us with one final, very exciting question. Now that we can finally listen to them, what other secrets are time crystals going to reveal?